Welcome freaking back, everybody. Today, we're finally going to discuss modular curves over the rational numbers. I'm going to do this pretty quickly today. Let's start off with a little bit of review. So let's review theorem 2 from the previous video. It says, let n be a natural number and let h sub q be the Galois group of q adjoin the j invariant and the n torsion of the universal elliptic curve E sub j over q adjoin j. There's an isomorphism rho from that Galois group H sub q to GL2 of Z mod NZ. It's the first thing. Secondly, and maybe a little bit more pertinently, if we let bold K be an intermediate field of this extension, Q adjoin J, and the n torsion over Q adjoin J, and we let just sort of regular K be the associated subgroup of the Galois group H sub Q from the Galois correspondence from Galois theory, then bold K intersect Q bar equals Q if and only if det rho, thought of as a function on K, surjects onto Z mod NZ cross. In other words, bold K is the function field of an algebraic Q curve if and only if det rho surjects as a function on K. Okay, armed with this knowledge, we can finally describe x sub 0 of n and x sub 1 of n as algebraic Q curves, not just as curves over the complex numbers. Recall from my video, Complex Function Fields of Modular Curves, released a few videos ago, the functions f sub 0, f sub 1, and j sub n. These were various special functions that were weight 0 and invariant under various special congruent subgroups of SL2Z. I'm not going to rehash the definitions here. Go ahead and watch that video if you haven't yet. Mainly, though, let's consider the intermediate field extensions of this extension we're concerned with, Q adjoin j and the n torsion over Q adjoin j. Given by bold K sub 0 is Q adjoin J and F sub 0. Bold K prime sub 0 is going to be Q adjoin J and J sub n. Remember, J sub n was just the J invariant whose argument has been scaled by n. And bold K sub 1, which is Q adjoin J and F sub 1. Now, you might remember, these might look familiar to you. We looked at these exact extensions if we replace Q by C, okay? These are analogous to the function fields of the complex modular curves x sub 0 of n and x sub 1 of n from proposition 1 in this video here that I referenced. Okay, well, that's kind of no accident. So let's piggyback off that complex case and see what kind of results we can get. Much like, and in fact, partially because the complex function field of x sub 0 of n is just C adjoin j and f sub 0, and we saw it was also C adjoin j and j sub n, we find that the same thing holds true over Q. In other words, we find that bold K sub 0 is bold K prime sub 0. We find that these two fields are the same. Okay, so that matches what happened in the complex case. All right, and you can also show pretty quickly that det rho restricted to K sub I surjects onto Z mod NZ cross for I equals 0 and 1. What are these K sub I's? Well, you have, I guess I should have written K sub 0 and K sub 1 here. K sub 0 and K sub 1 are the subgroups of H sub Q corresponding respectively to the intermediate fields of bold K sub 0 and bold K sub 1 under the Galois correspondence from Galois theory respectively. Okay, so you have the determinant of rho surjecting on the subgroups of H sub Q corresponding to these bold K fields. Well, that puts you in a situation to use theorem 2. By theorem 2, these fields must be the function fields of non-singular projective curves over Q. Let's call those curves x sub 0 of n sub a and x sub 1 of n sub a for algebraic. Okay, so again, just let's go back to theorem 2 and let's see what I'm talking about. I've got this surjection of det rho on my subgroup corresponding to the field extension of the Galois group H sub Q. And so I know that my bold K sub 0 and bold K sub 1 are function fields of algebraic Q curves by this theorem. Okay, so what's the obvious question? The obvious question is, well, you named these x sub 0 of n sub a and x sub 1 of n sub a. Presumably there's some relationship between these and x sub 0 of n and x sub 1 of n. What is that relationship? Well, here's the final connection for the day. Let's denote by x sub 0 of n sub ac and x sub 1 of n sub ac the complex curves consisting of the C points, the complex points, satisfying the Q polynomials cutting out x sub 0 of n sub a and x sub 1 of n sub a. Remember, these are algebraic Q curves. They're cut out by polynomials over Q. I can certainly look at the set of complex points satisfying those curves. And I'll name them these guys. I'll add this extra subscript C to that notation. And so what's going on here is there's a theorem from algebraic geometry that kind of quickly guarantees you that up to C isomorphism, the complex points on x sub 0 n sub a, those are just the points of x sub 0 of n. And similarly, the complex points on x sub 1 of n sub a, those just constitute x sub 1 of n. So in other words, I've got these curves over Q, right? If I look at their complex points, not just their rational points, but their complex points, I recover the old complex modular curves x sub 0 of n and x sub 1 of n, which is pretty neat. And so from here on out, we can sort of describe and think of x sub 0 of n and x sub 1 of n as modular curves over Q whenever it's convenient for us to do so, which it will be frequently. Okay, and so starting next time, I will begin looking at these modular curves as Riemann surfaces, and we'll discuss that briefly. So thanks for watching, and I'll see you then.